Welcome to Nerdy Nisa. Today we're going to be looking at electrolytic cells. Now, electrolytic cells are cells that take advantage of non-spontaneous reactions. So they're different to galvanic cells that are looking at spontaneous reactions. So these reactions are not ones that ordinarily happen when these two substances just come into contact. So, what electrolytic cells are doing is they're taking electrical current and passing it through these substances to kind of kickstart the reaction. So, what they're essentially doing is they're taking the electrical energy that you get from the current and they're converting it into chemical energy that can then be used within these substances for the redox reaction to take place. Cool. Now, there are two main types of electrolytic cells. There are molten cells and aqueous cells. Those two cells essentially are ones where there are free ions that are ready to roam. Free ions are the most important part of an electrolytic cell because that's what completes the circuit. This is because the ions are able to move from one electrode to the other in order to allow the circuit's completion. So molten substances are when a substance is really melted down so that the ions are broken out of that structure and are able to move around within that solution. And then aqueous solutions are ones in which the ionic substance has dissociated, so its ions have been broken up and it's within water, it's in an aqueous solution. Let's look at molten electrolytic cells. For an example, let's say that we have zinc ions and chlorine ions as our molten substance. Now, this is not a spontaneous reaction. Zinc would need to gain electrons because it's currently positive, but it doesn't want to do that. It doesn't attract electrons strongly, so that's unlikely to happen. And chlorine would need to lose electrons because it's currently negative, but it doesn't want to do that either because it attracts its electrons really strongly. So we've got a very non-spontaneous reaction on our hands. So let's imagine that in our beaker, we have those zinc ions and chlorine ions as part of our molten substance. We can say that the two electrodes you see here are something like platinum because platinum itself will not partake in the reaction, so it's a pretty good electrode to use. Now, if you look at the way that this is set up, you have the two electrodes that are connected to different terminals of the battery. This side is more positive and this side is more negative. That's going to result in this electrode being a positively charged one on the surface and this one being negatively charged. That's because electrons are going to somewhat move from this electrode to the next, or for at least the beginning part of the reaction. So we've got electrons moving, so the left has an electron deficit, the right has an electron surplus, so we've got two charged electrodes. Now, charged electrodes is where this starts to get interesting. Because the electrode on the left is positive and my chlorine ion is negative, it's going to be attracted all the way up to that electrode. So now my chlorine ion over there is attracted there. And that electron is very strongly attracted now to that positive electrode. So my electrode's going to yank off my electron and take it for itself. That electron's going to travel through my circuit, through that same external circuit, and go all the way to my other electrode. Now, because my other electrode is just gaining all of these electrons and it's all negatively charged, my zinc ion, which is positively charged, is now going to make its way down to this electrode, right? I can have my zinc ion over here. Now, my zinc ion is thirsting for those electrons because it's so positive. So as those electrons come down, it's gulping them up and it's going to take those electrons for itself. Now, because on the one side you've got oxidation happening and on the other side you've got reduction happening, you have a reaction on your hands. And what's going to happen is as my chlorine gains electrons, it's going to form a chlorine gas because it's being reduced. And as my chlorine loses electrons, it's going to become chlorine gas. And as my zinc gains electrons, it's going to become zinc metal. And it's going to pretty much form nicely on this electrode. Now, because we know where reduction and oxidation are taking place, we know that we can finally label our electrodes. So I know that this electrode over here we have oxidation taking place because chlorine is losing electrons. So this over here is my anode. And over here, I have my zinc that is being reduced. So because it's gaining electrons, so this is going to be my cathode. A way you can remember that is an-ox, because anodes go with oxidation, and red cat, because reduction goes with the cathode. Now, aqueous electrolytic salts work largely the same. So if I have something like a copper chloride solution, so I have copper ions and chlorine ions, and they're my solution that's chilling in my beaker, a similar thing's going to happen. I'm going to have one electrode going to become more positive because it's at the positive terminal, and my other electrode's going to become negative. The positive terminal one is going to attract my chlorine ions because they're negative. Over there, they're going to lose an electron, similar to what happened in the previous example. That electron's going to go, it's going to travel through my external circuit, and it's going to end up on the other electrode. That negative electrode is then going to attract my copper ion, which is going to move over to that electrode. And when my copper ion is there, it's going to gain 2 electrons. And that's going to form copper metal on this electrode, and on this electrode we're going to have chlorine gas bubbles forming nicely. So it's a very similar mechanism, but the only thing that we need to consider is how does water play a role? Because water is also a species that's chilling within this beaker. So it's also something that's kind of competing with the substances inside. And the way you're going to see this is that water is actually going to want to be oxidized as well. If we look at our standard electrode potential table, the two substances that we've been talking about is we've been talking about our copper substance and we've been talking about our chlorine substance. So we can look at those over there. Now we know that the reaction we're talking about is the non-spontaneous one, in which we're talking about the copper ions and the chlorine ions doing a redox reaction together. Now with non-spontaneous reactions, the reaction that always takes preference is the one that's closer together on the table. You don't want things that are too far apart because those have too much energy involved. For spontaneous reactions, you love them because they've got so much energy, they're bursting to release it, they're bursting to do the reaction. But here, because we have to spark the reaction, it takes too much energy to do all those high energy reactions. So we want ones that have substances close together on the table. So notice, water as a substance is right over here. So in terms of being an oxidizing agent, we see that it's closer to the copper rather than the chlorine. So the actual reaction that we would be able to observe is the chlorine ions and the water, and the water over here. So what that essentially looks like is you have your chlorine ions coming on the one side, my chlorine ions at my reduction, they're gaining all of my electrons, whereas on the other side, I'm going to have my water, which is then going to become So let's look at our standard table of electrode potentials. The two substances that we've been generally talking about today is we've been talking about our chlorine ions and up here our copper ions. Those are the main ones. That's our non-spontaneous reaction. Now the thing with non-spontaneous reactions when looking at this table is the one that's going to happen is going to be the one that's closest together. We don't want anything on far ends of the spectrum because that means you have a really weak oxidizing agent and a really weak reducing agent. Remember, when you have things far away, when you're talking about a spontaneous reaction, that tells us that you have the strongest ones of each kind. But because we're talking about non-spontaneous reactions, and we're inherently talking about weak oxidizing agents and weak reducing agents, you want two substances that are close together, because that also means that the threshold of energy you need to kickstart the reaction is less. So you want substances that are closer together. Now, if I look at where water fits in, water is chilling right over there. And the upsetting part is that what is closer to chlorine is than what is closer to copper rather than what chlorine is to copper. And that's really upsetting because that means that water's actually going to be oxidized in preference to chlorine because it's closer to copper, which means that the energy to make this reaction happen is actually less than the energy that would be required to make this reaction happen. Cool. So what that essentially looks like on our diagram is that our copper reaction would stay exactly the same. This reduction would stay the same. But on our other electrode, on the electrode on the left, what's going to happen here is my water's actually going to be oxidized. It's going to give up about 4 electrons or so. And what that's going to result in is oxygen gas forming over there and a couple of hydrogen ions. The way I can see this is by looking at the half reaction stated on this table and seeing that when I have my water, it then becomes my oxygen gas, my hydrogen ions, and my electrons. So that's essentially the worry when it comes to the aqueous cells, and the reason we split it from your molten cells. It's because water becomes a competing species within the beaker. So, if I wanted the copper-chlorine reaction to happen, and I actually did want that functioning electrolytic cell, the solution would be to increase the concentration of my chlorine ions. Concentration. Ooh, that doesn't fit. But of my chlorine ions. The reason that that's incredibly important is because by Le Chatelier's principle, when there's an increase of concentration of my chlorine ions, my system's gonna feel uneasy. It's gonna want to rebalance itself. So it's gonna work really hard to decrease that concentration. So it's gonna start oxidizing that concentration just so it gets it back to where our standard conditions are. But when it kind of gets back to standard conditions, water is then going to surpass it because at standard conditions, water is oxidized in preference. So the best thing you can do is just increase that concentration to the best of your ability and use up as many chlorine ions as you possibly can. I hope that this video helped young scientists. If not, and you have any questions, please leave them in the comment section down below.